last time we talked about phase lattices. And so I showed you several properties of phase lattices, and one thing that I told you I was going to explain to you today is why, if you take the phase lattice of a polytope and you turn it upside down, that's also the phase lattice of a polytope. And so what we need is a construction that will take a polytope and kind of turn it around. And this is the construction of the polar polytope, or dual polytope, and that's what I'm going to talk about today. So these are also called dual polytopes. And the motivating example we already discussed. So maybe we have the cube, and then the dual polytope to this is the octahedron. And maybe the easiest way to draw it is to put vertices at the center of each face of the cube. Maybe I can do this. Something like that. Forget about this point here. And so this is more or less what we want to generalize today. Start with the polytope P, and we're going to define a polytope called the polar, and then order P with a little triangle on top. So let me just give you the definition and then prove some properties. So let's say that P is either a polytope or just any subset of R to the D. Okay, so maybe a polytope. Or maybe it's not a polytope, maybe it's something else. Or some other subset. But we mostly care about the case of the polytope. Let me say the polar of P is the following thing. We denoted P with a triangle. And this is the set of points C and R to the D such that Cx less than or equal to 1 for all x in D. Okay. Now, there's something important that I want to discuss, which is that actually I find it useful to look at these two pictures on top of each other, but they don't really live on top of each other, they live on different spaces. Okay? This is a subtle point, but it's kind of an important point as you go into this later. Really, P lives in R to the 3, and this red polytope really lives in a different space, which is actually the dual space. Now, do you know what is the dual space of a vector space? Maybe some of you, maybe not all of you. So, we will do a little parenthesis here. If you have that V is a vector space over, we could do this over any field, but really we mostly care about the reals, so let's do it with real vector spaces. Then there's something called the dual vector space, and this is the space of linear functions on V. Okay. Or, okay, so let me just write this: linear functions f from V to R. Okay? Now let me say a couple of things about this. One thing is that really you can tell a vector space by its dimension, as long as you know the field that it's over. So if it's of dimension d, then every d-dimensional, all d-dimensional real vector spaces are isomorphic. And since to define a linear function, you just have to define what it is on the basis, that means that if this thing has dimension d, this also has dimension d, which means that really, in some sense, they're kind of the same, they're isomorphic vector spaces. But sometimes it's useful to keep the distinction. Okay? And I don't know if you've noticed that I keep talking about functionals in this class instead of calling them functions. And you might be confused if you're not used to this, but the thing is that these are the things that are called functionals. Okay? But I mean, the point is that really, as vector spaces, this is isomorphic to me. Okay? And so P, the polar of P lives in R3 dual, which is kind of another copy of R3, but we want to keep it different. And one distinction that you want to make here, I mean, the thing is that if you look at this, really, the most natural way of thinking about this is that C is acting as a linear function on X. Yeah? So what we have really is what's called a pairing between a vector space and its dual, and C is really acting as a linear function on R, and we're considering the linear functions that send X to something less than or equal to 1 for all X in P. So really it's more natural to make this live in the dual space. To make this maybe a little bit more concrete, if you're not used to this point of view, think about this. If X is a column vector, then what do you want C to be? C should be a row vector, so that you can multiply C and X. Okay. And so one way that you might want to think about this is that the R to the D that we're used to thinking about in this class is column vectors, and the dual space consists of row vectors. So that's maybe a more concrete way of saying what I'm saying. If it's possible to say everything just by talking about dot products instead, but I think this is a useful thing to see and to keep in mind. Okay. So any questions about the definition of polar? Okay, so maybe we should try to do an example before we continue. So let's say that P is this triangle here. And I say that this is 1 and this is 1. Okay? So then what is the dual or the polar? Okay, well, we want things that when you take the pairing with 1, it should be less than or equal to 1. Okay? This is the point 0, 1. So when you take this, want to think about this as a dot product, then really what this is saying is that if you put 0, 1 here, what you're saying is that y should be less than or equal to 1. Okay? So this point here gives me the restriction that y should be less than or equal to 1. So it should be on this side. Okay. Now what about this point here? Well, this point gives me the restriction that x should be less than or equal to 1. So I'll make it something like this. X should be less than or equal to 1. Okay. Now what about this point over here? What does this point tell me? Here I'm taking the dot product with a half comma a half. So it tells me that x over 2 plus y over 2 should be less than or equal to 1. But if x is less than 1 and y is less than 1, then x over 2 plus y over 2 is less than 1. Okay? So this doesn't really give us any new restrictions. And this is an important point, that actually if you already have the restrictions on the vertices, then the whole segment between them doesn't give you any new restrictions. Okay? And basically that's true for the whole thing, that if you want to consider the restrictions of all the blue points, you just have to consider the restrictions of the vertices and see what those give you. We'll prove this, by the way. We'll prove this in a second. But what is this saying? This is saying that I'm taking the dot product with 1, 1, so it's saying x plus y less than or equal to 1, which looks like this and like this. Okay. So that means that the polar is all of this stuff. Agree? Okay. So that's an example of polars. And you see it's not a polytope, so this is something that maybe should worry you already, because I'm calling it a polar polytope and it's not a polytope. So we'll have to figure out what happened. ¿Esto? Okay. Actually, I'm going to do a trick here. I'm going to impress you with my... Well, okay. Let me make some statements and then we'll see if I need this or not. So, here. Let's say that you have polytopes P and Q. Now I think actually I'm going to erase this. I don't need this. And what I need is this. So P and Q are polytopes. So let's make a bunch of statements. First, if P is a subset of Q, then P dual is a superset of Q dual. Okay? This is actually very easy, because if you go from a smaller polytope to a bigger polytope, then instead of having fewer restrictions, you have more restrictions, and that means that your set becomes smaller. So that's a proof. P is a subset of P dual dual. You see that right away? I think this one is not obvious but easy, so we're going to make this a... If you just write the definitions, you'll see there's nothing to say here. This is very easy. Third, if 0 is in the polytope, then P is equal to P dual dual, or P polar polar. And this is a little bit more what you're used to. You're used to the fact that the octahedron is the dual of the cube and the cube is the dual of the octahedron. So generally, when we talk about dual things, dual is usually an involution where if you take the dual of the dual, you get what you had back. And this says that that's true as long as 0 is in the polytope. Here, I'm going to ask your help because the book puts this condition, but I don't think you need this. So I'm going to do the proof and you tell me if I'm lying, but I think you don't need this. So it says if P is the convex hull of V, then P dual is given by those A such that AV is less than or equal to 1 for all vertices V. So what this says is that you don't have to check the condition for every point in the polytope, you only need to check it for the vertices. Okay, and then finally, if, and again, the book has this, but I don't think you need this. So remember what this means is that the inequalities are given by 8x less than or equal to 1. Then P dual is given by this. Like this. Now, This is not. You see what I'm fussing with is what the order. I'm trying to figure out if it's 1.c or c.1. But you see, if you want to multiply on the left, then c is a row vector, which means that I should multiply row vector times column vector. So it should be c.1. So c.1 should be equal to 1. Okay? Now, if you think about this, what are we doing here? When you multiply a matrix A times a row vector C on the left, what you're doing is that you're taking a linear combination of the rows. Remember that we discussed that if you took a matrix A and you multiply it by a column vector on the right, then you were taking a linear combination of the columns. If you take the transpose of everything, you see that if you now multiply on the left by a row vector, then you're taking a linear combination of the rows. Okay. And so here what I'm saying is take linear combinations of the rows which are positive and the coefficients add up to 1. And that's precisely our definition of convex combination. So it's a convex hull, but it's a convex hull that looks a little bit different because it's on the left because these are row vectors. Okay. And this is why we're in the dual space. So that is a row vector. So this is really like you can think of this as the convex hull of the rows of A. Okay? Okay. So that's the theorem. That's the main goal that I have for today, is to prove this theorem. And I think maybe before we continue, let's just make this very concrete in this example. Okay? So let me just quickly do the example of these dual polytopes, where now I'm going to follow my instructions and draw them separately because this is one space and this is the dual space. Okay. And so this is P, and so P we can write as the convex hull of 1, 1, 1. We already did this, but I'm going to do it again anyway. So these are the vertices, and the inequalities are given by saying, for example, x is less than or equal to 1, minus x is less than or equal to 1, y is less than or equal to 1, minus y less than or equal to 1, z less than or equal to 1, and minus z less than or equal to 1. What am I saying here? See, I cannot multiply these matrices. That's why I have to get the order right. Actually, I need to multiply on the left. And now what is this one? This is B dual. And see, actually, so what is this? This is the convex hull of the rows here. So let me write maybe rows of 0, 0, 1 1, 0, 0 minus 1, 0, 0. No. I get confused with this dual thing also, but you get used to it. 1, 0, 0 minus 1, 0, 0, 0, 1, 0, 0 minus 1, 0, 0, 0, 1, and 0, 0 minus 1. Okay. And this is given by the inequalities are x, y, z times this matrix over there, 1, 1, 1, 1, 1 minus 1, so on. Like that, right? But one thing that you should realize actually is that in this space, I write things as convex halls of columns, and the inequalities I write as ax less than or equal to b. Which means that I don't like how I wrote this because I don't want it to be written in this way. I should really flip this equation over. Okay? So let me just rewrite this, but in the correct shape, because I have it in the dual shape. I wonder if I can flip this. Let's try.
¿Y eso? ¿Y lo verdecito no es para girar?
Ah, sí, sí, sí.
¿A seleccionarlo?
¿Qué pasó? ¿Está bien? La rendidora así voltearla. Así, ¿no?
No, lo que yo creo con lo verde que te sale encima, seleccionarlo.
Ah. Ay, así. No. Dejemos así. Okay, so is it okay now? No? Right, and why do I transpose? Because this is a vector that lives in this space, and therefore it's a column vector. Thank you. One thing you might realize is that so column vector. Yeah. If you look at the notes, you see that I got lazy and I did it both as row vectors and I revetted it. And I'm improvising now. But anyway, it's good now. And you see that the point of this statement is that if you write P as a convex Hall of things, then for the P polar, the inequalities are given by the exact same matrix. And if you write P in its inequality form, then for P polar, the convex Hall is given by the same matrix. That's the point that I wanted to make. Taking a little while, but okay. So let's prove this. So let's prove this one. If 0, 0 is in the polytope, then P is its own double dual. Okay? Okay. So P dual is the C such that Cx less than or equal to 1 for all x in P. Okay? What's P dual dual? It's, you see now what I want is, for the dual dual, I want to take the pairing with C, so I want this to be column vectors again. Okay? And maybe, so what do I get? I get y such that Cy less than or equal to 1 for all y in P dual. Okay? And this is the same thing as saying y such that.
No, for all C in P dual. For all C in P dual. Yes.
In the second C.
For all C in the dual, thank you. Okay, and so what this is what is it that I want to say here? The y's such that if Cx is less than or equal to 1 for all x in P, then Cy is less than or equal to 1. So now let's do the following thing. I told you that one inclusion is very easy, and it is true, I'm not lying. P is included in this, that's just straight from the definitions. So what I need now is to show that this is contained in this. So suppose that I have a Q in P dual dual, but Q is not in P. Okay, and let's find a contradiction. So what does it mean for Q not to be in P? Okay. Well, we know that if a point is not inside a polytope, then some inequality certifies that. So maybe I can draw a little picture here. Here's my polytope, and then maybe P is outside here. And so we already showed, this is one of the Farkas lemmas, that if P is not in the polytope, then you can find an inequality that shows that, right? And one way of saying that is that you can find a hyperplane that separates P from the polytope. So let's consider that, let's call this thing C dot x equals C0. So if we do that, then so let's this separate Q from P. In other words, we have that C dot Q is bigger than C0 and C dot P is less than C0 for all P in P. Okay? Okay. What I want to do now is divide by C0. But if I want to divide by C0, because these are inequalities, I should find out what sign C0 has. Can you tell me what sign C0 has? Is C0 positive or negative? We haven't used that zeros in the polytope. And if zeros in the polytope, then according to this, C dot 0 is greater than C0. So let's say that because 0 is in the polytope, then when I plug in P equals 0, I get that 0 is less than C0. Right? It's the only place where I'm going to use that 0 is in the polytope. So I can take these inequalities and rewrite them as C over C0 dot Q is bigger than 1, and C over C0 dot P is less than 1 for P in the polytope. Right. So now, if you look at the second condition, what is it saying? It's saying that C over C0 is in the dual. C over C0 is in the dual, right? And then, why is that a problem? Because C over C0 is in the dual, Q is in the polytope, and their dot product is bigger than 1. That can't be. Because the dual is defined to be those things such that when you take the dot product with something in the polytope, you should get something less than 1. Let me spell it out a little bit more. C over C0 is in the polytope, and we know that in P dual, Q is in P, and these imply that C over C0 dot Q is less than or equal to Q.
No, Q is not in P. In the P double dual.
Sorry, Q is in P double dual. Okay, and then that means that Q. Okay, so Q dot C dot this is C over C0 is less than or equal to 1. So it's less than or equal to 1 and it's bigger than 1. That's my contradiction. Okay? So that's the proof. So it's not too hard. And now we have maybe the nicest property, which is that the dual of the dual is the polytope itself. Okay? Any questions about this proof? Good? Okay. So, part D. So this is where I'm going to claim that this hypothesis is not necessary. So if I finish this proof and you haven't stopped me, then that means that we don't need that hypothesis. Okay? Watch carefully. If 0 is in the interior of the polytope and P is in the convex hull of V, then P dual consists of the points such that A dot V equals 1 for all V in V. Less than or equal. Thank you. Okay. So proof. Well, what is P star by definition? It is the A such that A dot P is less than or equal to 1 for all P in P. Okay? And that means that if you satisfy this, then clearly you satisfy this. If you dot product with any point in the polytope is less than or equal to 1, then that's true of the vertices. Okay? So that's a proof of this direction. There's not really anything to say here. Now for this direction, let's suppose that it's not true. So let's suppose that we have a point A such that, so let's see, let A be such that A dot B less than or equal to 1 for all V in B. Okay? And suppose that A dot P is greater than 1 for some point in the polytope. Okay? What I'm going to say is this. Consider the linear function A dot something, A dot x. Okay? The linear functional A dot x is maximized where? In some face. We don't know which one that face is, but there is a face. We call it piece of A, and that's where this is maximized. It's maximized at the face piece of A. Right? Now, every face has a vertex. So let's say that let B be a vertex of that face, piece of A. Then A dot that vertex is the maximal value of A dot anything in the polytope, which means that it's greater than or equal to A dot P, because P is in the polytope, and that means that it's bigger than 1. And that contradicts this. Right? You believe it? Why aren't you convinced? I believe it, I'm convinced. If you decide that you don't believe it later on, let me know, but I believe it. Okay? Last part. If P equals O. So this one also has a hypothesis that we don't need. So if P is equal to P of A, comma 1, and this is a vector, right? This is the 1's vector. Then P dual is given by this. And this is the convex hull of the rows of A. Okay? So let me tell you right away why we don't need this hypothesis. Because actually this follows from this. Okay? Because the inequalities of the polytope P are AX less than or equal to 1. Certainly if X is equal to 0, then A dot 0 is 0, which is less than or equal to 1. So that means that 0 is in the polytope. And if it was in the interior, then it would have to be on a face, which means on one of the inequalities. But all the inequalities are of the form A dot X equals 1, which 0 doesn't satisfy. Okay? So this condition implies this one, and that means we don't need this one. No doubt, right? Sometimes books have mistakes. It's okay. We're all human. Okay, so we're going to prove this. So again, there's two directions, and one is pretty straightforward, and it's from here to here. So this one is easy. Basically, you know, well, just write down the definitions, and you see that it's very straightforward. And this is the one that is tricky. So let's take a point in the dual polytope. Now, here, I want to say this. P is in the dual polytope. So what is the dual polytope? The dual polytope is those A's such that their dot product with anything here is less than or equal to 1. But what does it mean to be here? It means that, well, so let me just write this. So if X is in P, then A dot X is equal to 1. And that's what it means. But now, saying that X is in P is saying that AX is less than or equal to 1. So what this is saying is that if the A is such that AX is less than or equal to 1 implies that AX is, by the way, this was less than or equal. Okay? That's what the dual is. The point. The vectors A is such that anything that satisfies AX less than or equal to 1 also satisfies little AX less than or equal to 1. Okay? Now, if you remember, this is actually exactly what one of the Farca's lemma says. One of the Farca's lemmas, which is Farca's lemma 4, says if you have a polytope, okay, given by some inequalities, and if you have some inequality that holds for that polytope, then that inequality has to be a combination of the inequalities of the polytope. So let me write it out, because actually this is the Farca's lemma that we discussed the least. So if an inequality holds for a polytope P, then actually there's two cases. Either that inequality is a positive combination of the inequalities of P, which is what you should expect, right? P is described by some inequalities, and so it's just saying if you have some other inequality, then it should be a straightforward consequence of those basic ones. It should just be a positive combination. Either that is true, or the polytope is empty. That's what it says. Or the polytope is empty. So that's what Farkas 4 says, okay? And with that in mind, that's exactly the situation that we have here. Here we have a polytope, and here we have an inequality that holds for that polytope, right? It says if you're in the polytope, then you satisfy this inequality. That means that one of two things must be true. Either the polytope is empty, or this inequality is a combination of these ones. So let's do that. Either my polytope is empty, but can that be? No, because we already said that 0 is in the polytope. So this cannot be true. Or AX less than or equal to 1 is a combination of capital AX less than or equal to the Allman vector. Okay? So this is what we have. Let me, how am I doing with time, by the way? Okay. So we're saying that AX less than or equal to 1 is a combination of AX less than or equal to 1. Okay? How do we write a combination? Each one of these inequalities is a row inequality, right? And so if you want to write a combination of them,